Hello, everyone. Welcome to my talk. We're going to talk today about influences on nearshore Karenia brevis in Southwest Florida. First, I want to thank my co-authors, Dr. Medina, Nelson, and Milbrandt from University of Florida, North Carolina State University, and Sanibel Captiva Conservation Foundation, respectively. So before we talk about the science, I guess, I want to acknowledge the land and the waters that were included in this study. So the coastal waters of Southwest Florida, as we know it today, is rich in the history and modern traditions of First Nations. From the lands of the historic Caloosahatchee and Seminole, these lands are steeped in Indigenous history. We pay respect to their elders past and present, and extend that respect to their descendants, to future generations, and to all Indigenous people. We recognize the history of the land and extend our gratitude as we live and work as humble and respectful guests upon their territory. So harmful algal blooms, or HABs, emerge from this interaction between natural and anthropogenic processes. That algae is out there, and for the most part, it's the anthropogenic influences that kind of push it over the edge. And so as an example, here's, for example, Karenia brevis, or sometimes colloquially called red tide, blooms originate offshore in oligotrophic conditions in the Gulf of Mexico. If an upwelling event happens, or upwelling circulation event happens, then those blooms can be transported on shore. Once on shore, the terrestrial source of nutrients facilitates a bloom growth and maintenance phase, essentially. And you can see this figure here, this schematic model kind of showing a no bloom to larger bloom continuum, showing that, in no bloom conditions, things are kind of moving along. We have an ecology going on where zooplankton, atmospheric inputs, upwelling, you name it, things were kind of cycling through. And the small bloom condition, we could have some Karenia brevis out there chewing on some nutrients, doing its thing, not too innocuous, maybe a little bit, but in that larger bloom condition where there's essentially, once it gets to a certain phase, there's nutrient subsidies from the associating effects of the bloom. And so when we have high blooms, we typically have what's called brevetoxin being released from these red tide organisms that cause fish kills, which then those fish kills the dead fish decay and provide a nutrient subsidy and kind of fuels that bloom. So due to this highly complex nature of bloom formation, growth, and transport, the idea or the paradigm of more nutrients equals higher biomass really is overly simplified. But like I said before, once a bloom is transported near shore, if it's transported near shore, I guess you can say, nutrients from runoff can really stimulate that growth, and we have a substantial amount of runoff. So within Southwest Florida, Karenia brevis cell densities kind of follow this real seasonal pattern, ranging from kind of background conditions to not even knowing it's there to really high abundances. In this figure here, we have a time series of biweekly K. brevis abundances or cell densities from the harmful algal blooms observing system, or HAB-SOS. And so that, granted, this data is kind of a mix of response monitoring as well as systematic monitoring, but it does show some seasonality in it. Here's a table kind of showing the relative descriptions of kind of what the conditions are, the absolute kind of cell abundances, as well as the possible effects. And on the right there, you can see electron scanning microscope or even just light microscope images of K. brevis itself. And, essentially in the not present or background condition, there's really no potential effect of K. brevis there. If it is, it's minor. But once you get into those medium and high bloom events, you kind of really get into this in the condition where you have a release of brevetoxin, that toxin that this organism secretes or releases, and causing respiratory irritation, fish kills, and detectable coloration of the water. So this study is really motivated from Medina et al. 2020, where they concluded that K. brevis bloom dynamics exhibit this real regularity in time, and including a really strong seasonal signal with some influence of water quality there. The figure or the image there on the bottom shows the um, Franklin Lock or S79 structure, where on the left part of that, that's going to the estuary. On the right side, that's essentially going to the lake. And so this is the kind of salinity control structure where on the right, it's freshwater, on the left, it's saline. And so the objective of this study was really to evaluate the effect of seasonality and hydrodynamics along this freshwater to marine continuum of Lake Okeechobee to Caloosahatchee to understand K. brevis abundance within the estuary and the nearshore environments, and kind of understanding how that freshwater input really can drive things. And so using that HAB-SOS data, we combine that with other data types like discharge or lake stage in an additive, generalized additive model framework to kind of evaluate this. And so for those of you that don't know the Caloosahatchee Okeechobee connection, in the center of Southwest or South Florida, we have Lake Okeechobee, which is the largest lake in Florida, and I think it's the third largest in the continental U.S. And essentially, that lake is connected to the Caloosahatchee estuary through canals that were dug way back in the late 1800s, early 1900s. So historically, this wasn't really, the estuary wasn't connected to the lake. And you can see on that map on the left where we have S79 there, which I introduced earlier. That's that point where fresh water makes it into the estuary. And then you have on the far right, from the lake to the canal there, you see S77. That takes water from Lake Okeechobee, puts it in the C43 canal or Caloosahatchee River, makes its way to the estuary. And in between there is a pretty large watershed that contributes runoff. So back to the GAM framework here. So due to that seasonality of data and potential external drivers, we wanted to kind of look at the data a couple different ways. We wanted to see if there was any trend or long-term change in the K. brevis abundance data, if there was any seasonality and within year variation, and maybe a potential interaction of those two effects, and then explore potential drivers of water quality, discharge, water level, et cetera. So, and this equation here, you can see it kind of looks like a linear model equation, but this is actually a generalized GAM kind of model, how you kind of would write it out. And so you see beta 0 there, that is essentially your intercept. The F seasonal is the seasonal component. You have your trend component, the interaction of season and trend, and then a potential driver, and essentially an error term. So we're going to look at it 3 different ways. We're going to have 3 different models. The first one being a seasonal model, where it's just day of year and year as your seasonal and trend component in that interaction. Then we're going to add on the driver component of discharge from S79. And then building on that, we're going to use that first seasonal model and add on the driver of lake stage. And essentially the way we're thinking about it is that discharge from S79 provides some measure of freshwater flushing in the estuary and some seasonal hydrology that kind of is a culmination of water sources from the lake and from the basin. And so lake stage provides a similar metric of seasonal hydrology, but added a little bit of a benefit or a caveat of potential discharges from the lake. So when lake stages are high, we were going to see discharges to the estuary. Essentially, it's kind of what that indicates. So looking at a little specifics of the data, right? So K. brevis density data from the HAB-SOS program, like I said, we only looked at the spatially between 26 and 27 degrees latitude within 16 kilometers of the shore. That's consistent with Medina et al. And we only used data, we actually calculated that monthly mean of the surface water samples. So those collected less than 5 meters below the surface, and log transformed it and retained those zeros. And we only temporally looked at it between October 2012 to 2018. And that's because, like I mentioned earlier, there was some changes in sampling protocols, both from a response standpoint, but also from a systematic monitoring standpoint. So this seems like a period when it seemed somewhat was consistent of both. And to kind of really evaluate the three different models, we split the data randomly into training and testing data sets. So now that we talked about data, let's start modeling. So here's the seasonal model. The way we have it shown here is that on the top, we have the actual model that I introduced earlier, the standard kind of output table of a GAM. So we have the parametric coefficient, so that intercept term, as well as our smoothing term, so day of year, and that interaction term. In that table, you also see adjusted R squared, which is adjusted R square. And then you have deviance explained. And in GAM world or GAM speak, that's essentially R squared in linear model world. And so the plots there on the bottom, what we have is what's called effects plots. And the way that it kind of reads is it's the effect broken out by each term of the model, each smoothing term. And so on the left, we have day of year, the smoothing term for that. It's where we see, from 0 to 365 days, we see a significant dip there in the middle, and that's showing the effective day of year on K. brevis abundance, essentially. In the middle there is the year term, the smoothing term for year. So from 2012 to 2018, we have that. And then on the far right, that heat map looking thing is essentially the day of year interaction with year term plot. And essentially the yellowy colors are positive effects, the purpley colors are negative effects. And you can see that the positive effect kind of switches around through the time series, which is interesting in itself. Here's the season and discharge model. You can set up just like before on the top, there's the equation that I introduced earlier, the table with the parametric and smoothing terms, and then those effects plots. So the first two plots, day of year and year smoothing terms, remain the same relatively. They don't change much between these models. The next plot, that the third plot in, essentially is the effects plot for the smoothing term for S79 discharges. And you can see that generally the data is kind of grouped to the left of the plot a little bit, but you can see that as discharges increases, there's a potential negative effect on K. brevis abundance. And then on that last plot there is the similar plot to before, where it's the interaction term between day of year and year. So why is discharge so interesting and important here is, here's a trend analysis done by Dr. Nelson here, showing trends in discharges from the lake, the watershed, and into the estuary, both from a monthly perspective, but also from a seasonal perspective. And so you can see that discharges from S79 into the estuary typically increase or significantly increase in that September to December timeframe. This period also just so happens to correspond to the period where red tide initiates, quote unquote, the most frequently. So this is the period when blooms occur the most, the September to December timeframe, which just so happens to generally correspond to the start of our end of the wet season, early dry season. And the increases at S79 can generally be attributed to increases in discharges at S77. So as lake water management changes, water levels need to be regulated. This is the one mechanism to do so, where S77 is the outlet from the lake to the estuary. Here's the stage season and stage model as introduced before, that Y3 model. And again, that table is still the same or similar to all the other tables where it has the parametric and smoothing terms. And the effects plots, again, are relatively similar to where the day of year and year plots generally are the same. The one thing that's interesting is that third plot there is the effect plot of the lake stage smoothing term there, to where as lake stage increases, we see an increase in abundance of K. brevis in the estuary. and then eventually it tops off and drops off. And this is important because we actually detect a significant increase in effect of the model between 14 and 15 feet NGVD. That's the stage units. And again, the interaction of year and day of year plot remains relatively the same. So going a little bit more into that significant increase. So here on the top left is a similar plot to before. It's just the smoothing term for mean lake stage, the effect of that. And the red part there is essentially a significant change. So that's the period in which that it's not significant, or it's significantly different from zero. Which is interesting because in the 14 to 15 foot range, generally here the plot on the right is the water levels for the past 7 years, or during the period of record or period of the study, relative to the Lake Okeechobee regulation schedule of 2008. And so within that regulation schedule, there's various different what they call bands. And so you can be in a high water band, and that means you got to do move the water one particular way. If you're in a low water band, you can move the water a different way. Regardless, this is water level within the lake, and you can see that in the later years, so maybe post 2015, you can see that generally the orange and red colors are kind of a little bit higher than the earlier years, which is of significance and corresponds to the effects plots as well. So real quick, to compare the models to see which one kind of shakes out as the best, we have various different metrics that we kind of look at. But and if you just judge it by AIC, it would be season and lake stage. It does a pretty good job of explaining the deviance, and is it has a decent mean square error. One thing to note, though, none of these models really are significantly different, as that bottom table kind of really shows. And so in summary, this modeling effort suggests that the combined role of season and estuary flushing really has an effect on coastal red tide densities. And it corroborates past studies like Medina and others, but also some ongoing studies. And the current models, granted, GAMs in general are really not predictive tools per se, at least the way we set them up here, because they can't really be extrapolated outside their fitting period. But I mean, that's one limitation of GAMs in and of itself, but it's also a limitation of all models. But it does kind of give us an idea of the effect of different components of the data structure. So we can see a seasonal component, we can see a trend component, and then a potential driver component. So future efforts, we want to include some nutrient inputs to kind of really see how that improves model fit, and maybe potentially combining some of the models. So instance, discharge and stage go together and see how that works, because that's an integrated hydrodynamics view of things. And also expanding that period of record to evaluate changes in hydrology and water quality. We have a lot more data since 2018, obviously, and maybe unfortunately. I mean, there have been blooms more recently, so we could potentially expand this a little bit further. And so wrapping things up, I want to acknowledge the data sources, South Florida Water Management District and NOAA, as well as if anybody is interested in how this stuff was done, you can go to the repository on GitHub and dig into the code. And if you see any errors, let me know. Thanks a bunch.